So good afternoon, everyone. Okay, let's start our webinar on photonic technologies. First of all, I would like to welcome all of you towards this webinar. So this webinar is, as mentioned in the brochure, is intended to give some interdisciplinary research and development area related with the photonics. The first session of the webinar, we discuss holographic 3D rendering technology, in which basics of 3D graphics and basics of holography is discussed, such that we hope the session will shed some light on the development of real-time 3D holographic rendering. The second session is related with the nanophotonics, the interaction of light and matter, especially the interaction of light with the matter having refractive index variation, the scale of wavelength of light, such that the new phenomena and technologies arise from that one will be discussed during the second session. With this short introduction, I would like to introduce our resource person for the first session, Mr. Abhishek Rishikesh. Mr. Abhishek Rishikesh is a founder and CEO of AI Render Technologies, a startup based on Bangalore. This startup is related with the next generation video conferencing technique. Prior to this, he was an engineering manager leading the graphic architecture labs team at Intel. Also, he was one of the recipients of the second highest technical awards at Intel for his contribution to 3D graphics performance analysis. He holds an MS degree in computer science from Arizona State University. With this, I welcome Dr. Abhishek Rishikesh to handle the first session on holographic 3D rendering. Welcome, Mr. Abhishek Rishikesh.
Thank you, Dr. Sajeev. Let me share the screen. Let me know if it's visible.
Okay, it's visible.
All right. Good evening, everyone. Thanks a lot to the faculty and students at Government College, Karivattam, for providing me an opportunity to present here. And a special thanks to Professor Sajeev for coordinating this talk and a great introduction. So as you can see, here is our website of the startup, the video conferencing app, and the YouTube outreach link for your reference. Please give it a try. So, okay, what's holography? As most of you know, holography is a technique that enables a wavefront to be recorded and later reconstructed. A hologram is constructed by superimposing a second wavefront called a reference beam on the first wavefront, which is the wavefront of interest. This superimposition generates an interference pattern. This pattern is recorded on a physical medium, and that constitutes the first step or the recording step in holography. Now, the second wavefront, which is similar to the reference beam in the first step, eliminates the interference pattern and is diffracted to create the original wavefront, and that constitutes the second step or the reconstruction step in holography. Here is the agenda. Let's get to the topics. Okay, all of us have gone through the theory on diffraction in our schools, but just to recap, like diffraction happens when a wave faces an obstacle or an opening. The result is interference or bending of waves around the corners of the obstacle or through the aperture. As you can see, the light coming into a dark room from outside through the door is due to diffraction. The rays of sunlight filtering the clouds is a natural example of diffraction. You can see the diffraction for yourself. For example, like maybe like form a slit between your two fingers and use the torch in your mobile phone to illuminate the slit towards a wall. You can see the diffraction at the boundaries of the shadow created on the wall around the illuminated shape of the slit. Now, there are two main forms of diffraction. One is Fraunhofer and the other is Fresnel. When both the incident waves and diffracted waves are effectively plane, Fraunhofer diffraction occurs. Here, the distance from the source to the aperture and from aperture to the receiving point are large. It's quite large enough for the curvatures of the incident and diffracted waves, as shown here, to be negligible. When either the source of the receiving point is close to the aperture, either the source or the receiving point is close to the aperture, we have Fresnel diffraction. As you can see, the wavefront capture is significant. The curvature is significant and cannot be neglected. Now, this is how we record a hologram of an object. In this case, let's use FIFA World Cup as the object. The input laser beam is split into two beams. As you see, one of them illuminates the object directly. The other one is reflected from a mirror onto a photographic plate, as shown here, and it's called the reference beam. An interference pattern is created by exposing the film in the photographic plate to both the reference beam and the reflected beam from the object. So this interference pattern is recorded by the film in the photographic plate. And here is how the holographic display of the object is reconstructed. The hologram developed from the photographic film is exposed to a laser beam similar to the reference beam you saw in the previous slide. The resulting diffracted wave field produces a three-dimensional projection of the original wave reflected by the object. The viewer can see the virtual 3D projection of the object through the hologram. A real 3D projection of the object is also created. Now, let's take a look at the math behind holography. Here, the XY plane represents the plane of the recording photographic plate. The first equation shows UXY, or the complex amplitude of the reflected wavefront in XY plane reaching the photographic plate for recording. Phi xy shows the phase of the reflected wavefront, and AXY is a real function which helps to form the amplitude of reflected wavefront. The second equation shows U0xy, which represents the complex amplitude of the reference beam, in that A0 is a constant, mu and epsilon are spatial frequencies of reference beam in the XY plane, and they are represented by the third equation, where K is the wave number of laser light, and alpha and beta shows the direction of the reference beam. As we saw, the interference pattern is created by both the reference beam and the reflected beam from the object. The irradiance of the interference pattern is equal to the square of sum of amplitudes of reflected beam and reference beam, and the first equation here gives that. So that gives the representation of the hologram recorded on the photographic plate. Now let's look into the math for reconstruction of the 3D object projection from hologram. As we saw, this hologram is illuminated in the reconstruction process by a laser beam U0 similar to the reference beam. The resulting transmitted wave UT is proportional to U0 times the transmittance of the hologram at XY point on the object. The transmittance is proportional to irradiance IXY that we saw in the first equation here. So the second equation gives the resulting transmitted wave UT from the reconstruction process. Now, this equation resembles a diffraction grating, which produces a direct beam and two first-order diffracted beams on either side of the direct beam. You see, there are three terms here. The first one, which is proportional to U0, is the direct beam coming out of the hologram. The second term, which is proportional to UXY, forms the virtual 3D projection of the object as shown in the setup above. This is one of the diffracted beams that reproduce the reflected light from the object. And the third term, which is proportional to inverse of uxy, forms the real 3D projection of the object and constitutes the other diffracted beam. Now, with that, let's get to the second session for today, that is 3D graphics. Here is the agenda. Let's get to the topics again. Our universe exists in multiple dimensions, possibly more than 10. An average human being can perceive the world around him or her in three-dimensional space. Most existing computer applications visualize the space in 2 dimensions. In the last century, with the introduction of computer-generated graphics, many applications have started visualizing the world in 3 dimensions. Today, we are going to take a walk through the world of 3D graphics. Now, have you ever wondered how 3D games like Fortnite, Pokemon, Counter-Strike, City Racing, that most of you might have played, right? How do they work? How do popular 3D software that you have worked on, like AutoCAD, Maya, or Unity, or Unreal, bring 3D objects, models, and 3D world into action? A 3D game or a 3D world scene can be considered like a movie, which is arranged as a deck of frames, as shown here, or images, and they are played in sequence. Each frame is constructed by converting a world modeled in 3D to a 2D image, and this process is known as rendering. As an illustration, let's take a look at the rotating cube on the left side. Rendering basically converts the view of the cube from a particular angle and projects it in 2 dimensions onto the computer screen, as shown on the right side. In this section, we are going to get introduced to 3D coordinate geometry. Let's take a look at the simple 3D example, one of the simple 3D examples at your home. Here is a typical dining table. You can see the shape of the dining table is made out of multiple rectangles. For one of the rectangles shown in the previous slide as part of the dining table, let's now define the 3D coordinates. The rectangle has a length of 2 units and width of 1 unit. The rectangle can be split into 2 triangles. One of the triangles has the following coordinates in the XYZ coordinate space: 0, 0, 0, 0, 1, 0, and 2, 0, 0. And similarly, all the coordinates of the table can be defined. In this section, we will introduce you to the different spaces and the concept of transformations in 3D graphics. Primarily, there are 5 major spaces and 4 main transformations in 3D graphics. First of all, there is local space, which deals with the creation of local objects. Then comes world space, which positions multiple objects in a 3D scene. Then we have the view space, which sees the world from a viewer's or a camera's point of view. Further on, there is clip space, which clips the portion of the objects to be shown in the screen and adds perspective projection. Finally, there is screen space, which maps normalized clip space coordinates to a pixel on the screen, for example, like a mobile screen or the laptop screen. Now, let's first touch upon the first 2 spaces and the transformation between them. Think of local space as the 3D coordinate space in which a single object is created. For example, the tabletop in the example we showed in the last section is a local object in the shape of a cuboid and can be defined with its own 3D space with its XYZ axis and origin. Similarly, a table with tabletop and its 4 legs and an almirah can be considered to be part of a world space in a specific 3D scene where they are defined with a common global 3D space with a common origin and XYZ axis. The model matrix, which transforms local objects from its individual local spaces to a common world space, consists of transformations like translation, scaling, and rotation of vertices of these local objects. Now, let's see what a 3D transformation consists of. It's essentially a matrix toward vector multiplication. The transformation matrix, as you see here, is a 4 cross 4 matrix. The vector consists of contains basically a 3D attribute of a vertex of an object. For example, XYZ geometry coordinates. This vector is 4-dimensional or can be considered as a 4 cross 1 matrix for all practical purposes. The 3D transformation performs a dot product matrix vector multiplication of the 4 cross 4 transformation matrix with the 4 cross 1 3D attribute vector, in this case for the vertex geometry coordinates, to obtain a 4 cross 1 transformed matrix. And the same transformation is generally applied to all vertices of an object. The model matrix mentioned in the last slide performs a translation, rotation, or scaling, or a combination of this for all vertices of an object in a local space to transform it to the global world space. Now let's practice some of the concepts that we just learned. So here is a rotation using 3D transformation that's shown here. So let's take the top view of the tabletop in 3D that we had shown with the coordinates 0, 0, 0, 2, 0, 0, 0, 1, 0, and 2, 1, 0. Here we are trying to rotate it by 30 degrees in positive z-axis. That's in the xy plane. So let's identify the missing transformation matrix elements A, shown in the transformation matrix below, for vertex with coordinates 2, 1, 0. So the transformation matrix is shown here with the rotation parameters like cos 30, sin 30, cos 30, etc. And one of them is missing, which is A. And the 3D attribute vector is used for the dot product calculation, and the transformed vector is shown. So here are the options. The first one is cos 30, second one is sin 30, third one is tan 30, and fourth one is sin 60. You can mark your choices in the chat window in the Google Meet. It's probably take a couple of minutes. Here is the rotation in the axis shown. This is how it is rotated through the xy plane in z-axis. And here is the transformation matrix where one of the elements is missing. And here are the options. Please mark your options in the chat window in Google Meet.
You can mark your options in the chat window. Just Try to give your answer if it's right or wrong. So sin 30 is the answer to of them. Okay, sin 30.
Okay. So the options given are right. Yeah, sin 30 is the answer here. Basically, you multiply, do the matrix multiplication with the rotation coordinates between the transformation matrix parameters and the 3D vector parameters to get the transform vector. Now, the objects in the world space can be viewed from different angles. For example, we can place the camera on front, top, bottom, or sides or at specific angles. Here, you can see the top view of the two objects after transformation to the view space. View space is also called as eye space or camera space. Viewing the exterior through a window can best explain the transformation from view space to the clip space. This is similar to placing the objects in view space into the rectangular window of the world visible through a computer monitor. Some objects like the boundary wall in the picture shown here gets clipped. Some of the plants which falls within the boundary of the viewing window is included within the clip space and are shown completely in the picture, while some of the other objects like the gate and the kennel on the left and right sides of the viewing window respectively gets discarded. Screen space converts clip space objects to pixels on the screen. The screen may be of the resolution 1920 cross 1080 pixels for a laptop, or let's say 800 cross 600 or 480 cross 900 pixels for a mobile phone. We are going to view the orthographic and perspective projections and frustum in this section. To understand orthographic projection, let's consider Bombay-Pune Expressway and viewing it from a helicopter or let's say a drone. For most part, one of its lanes appear like two parallel lines at both sides of the road for a straight stretch of the road. This is an orthographic view of the road. Typically, orthographic projections are done for faraway objects. The orthographic frustum view shows shows the near plane and far plane parallel to each other, and most importantly, similar sized in terms of what can be viewed within it. Think of near plane as a computer monitor and far plane as the plane including the farthest object you can see within the scene, and parallel to the computer monitor screen or the near plane. The planes are near and far with respect to the viewer's eye or the camera position. The space between the near plane and the far plane is called a viewing box. The viewing box of orthographic projection is a cube-like frustum box. As you can see, the objects which fall completely within the viewing box, like the green cube, is completely visible and included in the view. The red cube which falls outside the view box is discarded, and the blue cube which falls on the boundary of the viewing box is clipped. Here is the perspective projection of the same lane from Bombay Pune Expressway. If you stand on the lane and view the far stretch of the straight road, as far as you can view, the two edges of the road seems to merge towards the far stretch as shown here. The distance between the edges seem to be wider towards you and seem to be closer towards the far end of the road. This is a typical example of the perspective projection and takes real life perspective view of the scene. If you have gone to a drawing competition for small kids, you can see most of the pictures, be it for roads or houses, are drawn as orthographic projections. Most of the engineering drawings are orthographic projections, whereas the great paintings of, let's say, Da Vinci or Picasso or Raja Ravi Verma capture perspective projections. Farther objects in orthographic projections seem to be same size as nearer objects, and that creates sort of a weird view of the scene. Now let's stand in awe of the simplicity of the frustum view of the perspective projection. Again, the laptop screen can be considered as the near plane, and the plane containing the farthest object in the scene can be taken as the far plane. The length and height of the far plane seems larger than the near plane. The four sides joining far plane and near plane are kind of trapezoidal in shape. Here again, the objects within the view box or clip space volume as it is called, like the blue cube, are captured in the view. The ones on the boundary, like the red cube, are clipped, and the green cube outside the frustum view is discarded. Now, there are three parameters that define a camera's viewing direction. Imagine a fighter plane. Let's consider the X, Y, and Z axis of the fighter plane as shown in the figure here. The rotation about the Y axis and in the XZ plane is called yaw. And the rotation about the X axis and in the YC plane is known as pitch. And finally, the rotation about the Z axis and in the XY plane is known as roll. The rotations can be in clockwise or anti-clockwise directions. Similarly, a camera can be rotated along this axis and positioned for a particular view of the scene with specific yaw, pitch, and roll parameters. Now, let's take a deep dive into depth. To understand depth, consider a chair that's behind a trolley bag or a paper on top of the chair. The portion of chair that's behind this paper or the trolley bag will not be visible, and hence that doesn't need to be rendered. The structure we use to record the depth of different objects to check which object is in the front of the other object is called depth buffer. The depth buffer has values ranging from 0 to 1 for all pixels on the computer screen. 0.0 here represents the near plane corresponding to the objects that are closest to the camera or the viewer, and 1.0 represents the far plane, which relates to the objects that are farthest in the scene from the eye view. So an object X, which is in front of an object Y, will have a smaller value of depth versus Y in the range 0 to 1. Before you receive any objects to render, all values in the depth buffer are initialized to 1.0, setting them as the farthest in the scene. Now, in the previous section on introduction to coordinate geometry, objects were shown to be built from multiple triangles. Depth corresponds to the Z coordinates of the vertices of these triangles. Now, let's consider a triangle from the upper left half of the chair, as shown here. Imagine a rectangle covering that triangle with its sides parallel to the length and breadth of the computer screen. For sake of simplicity, assume all vertices of the triangle have a depth value of 0.8 corresponding to their Z coordinates. So this triangle passes the depth testing, and corresponding locations in the depth buffer are marked as 0.8. These locations map to the imaginary rectangle covering the triangle. The depth test pass means this chair triangle will continue through further steps of rendering. Now comes a triangle from the trolley bag towards its bottom, which doesn't overlap with any portion of the chair. So this triangle also passes depth testing similar to the previous one, and the respective locations in depth buffer are marked with its depth value of 0.5. Now let's consider a triangle from the chair that overlaps with the trolley bag towards the middle of the scene as shown. Since this triangle is the one to reach depth testing first, it passes depth test and the corresponding mapping locations in depth buffer are marked as 0.8. And here comes a triangle from the trolley bag which overlaps with the previous triangle from the chair towards the middle of the scene. Note that the depth of the trolley triangle is 0.5 and it's less than the 0.8 depth of the chair triangle. So that also passes the depth test and the corresponding mapping locations in depth buffer are overwritten with its depth value of 0.5. On the other hand, let's assume the same trolley triangle came for depth testing before the middle scene chair triangle. It passes depth test and the depth buffer locations are marked as 0.5. Since the chair triangle came to depth testing after the overlapping trolley triangle, it fails depth test and its depth is as its depth is 0.8 and higher than the trolley triangle's 0.5. The chair triangle is therefore discarded from further rendering. Now let's play with stencils. Stencil is pretty much same as the stationary stencil that most of you had used in your schools. Typically, it's used for showing alphabets and numbers in a 3D graphic scene, and at the same time ensuring the background 3D graphic scene is rendered without any disruptions. Here are a couple of real-life examples of 3D graphics games that utilize stencil. As you can see on the left bottom corner, the player 1 Lakshman is being shown using stencil. Here, the alphabets in Lakshman are sort of carved out using the stencil, and the background 3D graphic scene of the game is visible through these letters, while the box containing the alphabets of Lakshman occlude the background 3D scene. Similarly, the stencil is used to showcase the options of different guns for the game player and the score as shown on the top right corner. Now, stencil testing is implemented using stencil buffer. It's similar to the depth buffer shown in the last section. Stencil values here of 0 to 1 are used in stencil buffer to indicate whether or not to render each pixel on the screen based on a stencil mask. All values in the stencil buffer are initialized to 0. Here is a stencil mask which shows the letter L in Lakshman. As you can see, the locations in the stencil buffer mapping to the portion of the 3D graphics game scene visible through the region of alphabet L are marked as 1, indicating its visibility. At the same time, the stencil buffer locations mapping to the brown box covering the stencil mask for letter L are all set to a value of 0, which indicates the mask will be occluding or covering the background region. So that's pretty much the world of stencil testing. Now let's see the dark side of backface culling. The most popular face culling method is backface culling. Consider the tabletop that we had seen in the prior sections. If the viewer of the camera is seeing the tabletop from the top view, the top face of the tabletop is visible and the bottom face of the tabletop is not seen by the viewer. The top face and the bottom face of the tabletop are rectangular in shape and are made up of 2 triangles each, as discussed in the previous sections. In order to perform backface culling, we assign a winding order to the vertices of each triangle. From the exterior of the tabletop, vertices of all triangles are numbered incrementally in a counterclockwise direction. The vertices are numbered in counterclockwise direction as if the triangle is facing you. As you can see, the vertices of one of the triangles on the top face of the tabletop are numbered from 1 to 3 in counterclockwise direction. Similarly, the vertices of one of the triangles on the bottom side of the tabletop are numbered from 4 to 6 in counterclockwise direction if you assume that triangle is facing you, in this case from the bottom side. But when you view it from the top, the winding order becomes clockwise. Now all triangles with clockwise winding order are culled, and rest of the triangles with counterclockwise winding order are retained and are visible. Hence, the bottom face of the tabletop, if not visible, is not visible, and only the top face is visible to the viewer. Now let's delve into one of the most important topics in 3D graphics rendering called rasterization. Most of you may be familiar with the raster scanning methods in older televisions. As we have seen in one of the earlier sections, 3D objects are made from 3D polygons, and 3D polygons are made from triangles, which are the basic building blocks of 3D objects. As you can see here, the tabletop is a rectangle, which is a polygon, and it consists of two triangles. Now, rasterization involves converting triangles of 3D objects in the 3D scene into pixels on the computer screen. The basic requirements for rasterizing two adjacent triangles, that's the triangles that share a common edge, involves it should not leave any holes, that is non-rasterized pixels between the two adjacent triangles, so that the rasterized area is completely filled, and no pixel in the rasterized no pixel is rasterized more than once. That is, the rasterized triangles should not overlap. In order to achieve these requirements, certain rasterization rules are established. One set of such rules is top left rule. It states that if a pixel is rasterized, if and only if its center lies completely inside the triangle, or its center lies exactly on the triangle edge, that is either top or left edge. In case of corners, the pixel center lies exactly on multiple edges, that is top or left edges. A top edge is an edge that is exactly horizontal and it lies above the other edges, and a left edge is a non-horizontal edge that is on the left side of the triangle. Now let's go through a rasterization algorithm. In order to reduce the number of pixels that need to be traversed as part of the rasterization for each triangle, the algorithm computes a bounding box for the triangle to be rasterized. Computing the bounding box involves finding the minimum and maximum x and y coordinates of the three vertices making up the triangle in raster space. Now, once you compute the bounding box of the triangle, the next step is to iterate only over the pixels within the bounding box to rasterize the triangle, rather than rasterizing over the entire set of pixels on the computer screen for each and every triangle. Rasterization checks whether each pixel in the bounding box is inside or outside the triangle using the rasterization rules we discussed in the prior slide. Now let's learn how to sample texture maps. First of all, let's see why do we need texture sampling. Let's take the example of a high quality 3D face like the one shown here on the right side. A typical high quality 3D face requires anywhere between 40,000 to 60,000 vertices or more when you capture it using a high resolution 3D scanner. If we were to color each vertex separately, it requires an RGB color value per vertex amounting to around 40,000 to 60,000 RGB color values. Now that takes a lot of space in the memory to store the values. Instead, let's consider a texture map. Think of texture map as a blanket wrapped over the 3D object. For example, consider the tabletop shown below. We can wrap it with a texture map of a, let's say, plywood texture as shown here. Typically, texture maps are stored as a single image or multiple images. Here, the plywood texture image is shown on the right and has a width of 400 pixels and a height of 200 pixels. The texture coordinates in the axis along the width or the x-axis are typically called the u coordinates, and the ones along the height or the y-axis are called v coordinates. UV coordinates are scaled from 0 to 1. Now consider the top facing part of the 3D tabletop object. The rectangular tabletop can be split into two triangles, and the XYZ coordinates of the vertices of the triangles are as shown below. Now, the vertices of the top right triangle are mapped to UV coordinates in the plywood texture image. For example, the top right corner vertex with XYZ coordinates 210 are mapped to a pixel location with UV coordinates 0.8 and 0.9 in the texture image, and the corresponding RGB value of that pixel is mapped as the color for that vertex. Similarly, other vertices of the triangle can be mapped to different UV coordinates in the texture image as shown here. The advantage with storing such a texture map is that it can be reutilized for texture mapping the same person's face or the tabletop in different scenes in 3D graphics application. Now let's get to the concept of shaders in 3D graphics. Before going into the shaders, let's see how a typical 3D graphics pipeline looks like. A 3D graphics application is fed by the game programmer or the graphics application programmer to the 3D graphics pipeline, which is implemented in both software and hardware. Different blocks in the 3D pipeline are shown here, and we have already gone through most of these blocks in detail in the prior sections. For now, we will focus on vertex and fragment shader blocks. Each block in the pipeline has a specific function like the rasterization or texture mapping, as we saw in the previous sections. Now, some of these blocks are programmable and can be customized by the game developer, like the vertex shader and the fragment shader. Mostly, the vertex locations and the pixel colors of each vertex and each pixel are independent of other vertices, and pixels are only dependent on the neighboring vertices or pixels. So the vertex and fragment shaders are highly parallel small programming blocks. Now let's see what's a vertex shader. It performs transformation of XYZ location coordinates or other attributes like normals of vertices of a triangles in a 3D object. It performs rotation, translation, or scaling or zooming or other similar transformations of the triangles. The transformations of triangles and its vertices were discussed in one of the previous sections. The diagram here shows the rotation of the vertices of a triangle. The vertex shader takes the 3D XYZ coordinates or other attributes of a single vertex as its input. Similarly, the output of the vertex shader consists of the transformed 3D coordinates or vertex attributes of a single vertex. The primary function of a fragment shader or pixel shader is to determine the final color of a pixel. The input to the pixel shader is the initial color of a single pixel. For example, it can be the color of the nearest vertex to the pixel, or it can be fed with a uniform color of the for the triangle. The input pixel is obtained after rasterization of triangles to pixels and possibly after depth and stencil testing, as shown in the diagram on the right. The output of the pixel shader is the final color of the pixel as shown in the diagram of the rasterized pixels of a triangle on the bottom right. The pixel shader may run the lighting algorithms or shadow algorithms, which can be seen in detail in future sessions. Now, lighting in 3D graphics is a comprehensive topic in itself. If you like the session, we can plan for a session on lighting related topics in the future. Here is the YouTube link for the 3D graphics topics covered in today's talk. Please check it out. പറയാൻ കുറച്ച് കാര്യങ്ങളും ചെയ്തു തീർക്കാൻ ഏറെയുണ്ട്. Thank you all. Now we can open the floor for questions from the audience.
Thank you, Abhishek, for the nice presentation. So the question session is open now. There is a question from Gauri Nandana. How to approximate a 3D shape to a grid?
Okay. So as you see, there are multiple steps involved in that. Basically, the transformations that we talked about, right? It transforms the geometry from the whatever the game developer provides. Let's say the 3D grid, right, of a tabletop. We had it has these different geometry coordinates and all. So during the rasterization step, right, each triangle in that you will determine a boundary box for that, and here is the screen or the grid. So when you determine the boundary box, you determine the x min, y min, and the x max, y max of the triangle that is covering the triangle. And then within that, you go from left to right in that bounding box rectangle and see if a grid point or a pixel lies within the triangle or not. The ones within the triangle are rendered onto the screen, and the ones outside the triangle are not rendered. So this is how you convert the 3D object to a grid on the screen. Hope that answers the question.
Any questions? Sakshay, can you explain how you can relate this to holographic 3D rendering, something like that?
Sure. So basically, once we have the 3D representation of the object, right, you create a holographic display setup wherein you first record a hologram of that 3D object by using the reference beam and the direct beam part of the laser beam. So the laser beam is split into the reference beam and the direct beam. The reference beam is reflected from the mirror onto the photographic plate, and it causes an interference pattern there by the reflected rays from the object coming from the direct beam. So that is recorded on that interference pattern is recorded on the photographic plate, and the film in the photographic plate is used as a hologram, which is again illuminated with a laser beam in the reconstruction step. And this laser beam is similar to the reference beam, and that basically causes a phenomenon similar to the diffraction grating, where three terms are formed as part of the illumination. One with where the direct beam passes through the hologram, which is this first component, and two other components where the first one is similar to U or the virtual image, and the other one which is proportional to U inverse, which is similar to the real image shown here. So this is how you will form the holographic display after the 3D formation of that object is, I mean, after you define the 3D coordinates of the object and record the hologram and reconstruct the hologram. Hope that explains it.
Okay. Is there any other questions? Okay, if not, let's welcome someone from student community to propose the vote of thanks, please.
Good evening. Today's session was indeed very informative. Thanks for taking us to the intricacies of the subject. I thank the resource person, Mr. Abhishek Rishikeshan, for handling this wonderful session on holographic 3D rendering. I thank the Department of Physics for conducting this webinar in association with the IQSC, Government College Karyavattam, for conducting this wonderful webinar. This session was indeed very informative for the student community. I would also thank the audience for their active participation in this webinar, for making this webinar a successful event. Thank you.
Thanks for the opportunity and thanks for being a wonderful audience.
Thank you. So with this, our first session ends. So I think we can start the second session. So I would like to introduce the resource person for the second session. The second session is on nanophotonics, light management at the sub-wavelength level. The resource person is Dr. Rajesh V. Nair. He's an associate professor at Department of Physics, IIT Ropar. He obtained his PhD from IIT Bombay. He was a postdoc fellow at the University of Twente, the Netherlands. He worked as a Dr. K.S. Krishnan Fellow and also as a Scientist D in BARC, Mumbai. He received a Swarna Jayanti Fellowship in Physical Science in 2020. He is a senior member of Optica and is awarded INSA Young Scientist Medal in 2015. His research is related with quantum and nanophotonics and also bio-inspired photonic systems. With this introduction, I welcome Dr. Rajesh P. Nair to handle the session on the nanophotonics, light management at the sub-wavelength scale. Welcome, Rajesh.
Yeah, thank you, Sajeev, for the invitation, for the introduction. Is my screen is visible?
Yes, visible here. Is it visible to all of you? I think someone say in the previous session the screen is not visible, something like that. Is it visible? Is it visible to me?
The screen is visible.
Okay.
Okay, good. So now I can't see anything or anyone. Okay, so if there is, Sajeev, you please message me or call me in case something goes wrong. Okay. Hello. Okay. Because I won't be able to see or anything from audience. Okay. So thanks for this opportunity and the invitations. Today I'll be talking about something what we understood or we learned about nanophotonics, which is a system or which is a field where you can manage light, okay, in a very different way using at the sub-wavelength scale, okay. So as you say, it's a sub-wavelength scale. It all depends on your wavelength. If you're interested in 1 micron or if you're interested in 2 millimeter, the structures will change accordingly, okay. And myself is Rajesh from the IIT Ropar in Punjab. It's one of the new IIT which government started in 2018. So we are just a 14 years old institution now in the extreme northern part of India. And so today you see this, there is a nice picture, right? It's everybody must have noticed in your life. It's a beautiful coloration which see in peacock feathers. And this is one of the best example of a nanophotonic structure, which even nature made it, or even in the biological world. Okay, and this is people try to mimic these structures to laboratory and for device fabrications. And this is what is we call nowadays bio-inspired photonics. And even Helbert Pact lab at United States has a dedicated research group on bio-inspired photonic devices. Okay, so nature does very complex structures which even we cannot make it to the laboratory scale now, even with this development. But they do. The nature does it so meticulously that and this kind of color you see is because of the structure. Okay, these are not color due to pigments like the color in your dress. Okay, and these are called structural colors. So I'll be talking something similar to this today and try to convince you some exciting things about this emerging field called nanophotonics. Okay, so my outline of my talk, I'll talk very brief about nanophotonics. I understood mostly students. I'll try to be light as much as possible. And I'll introduce something called a photonic crystals, a kind of a nanophotonic structures, and some of its properties. And then these are basically ordered system, like you see here. Things are quite ordered. And then I'll talk about what will happen if you introduce disorder in nanophotonics. Okay, so I'll tell you later what is order and what is disorder, what I mean by that. And I'll conclude my talk with what we learned. Okay, so these are some of the, this coloration actually you see because of the ordered things, and this coloration certain birds have due to disordered system in the structure in the surface with some short range order. Okay, so like nanophotonics is all about light management. Like every day we manage light some way or other, right? The way you see in your mirrors, or in the night you use lights, or you see the kind of the, you're giving listening my talk because of the optical fibers. That is another way to manage light. So in nanophotonics you manage light through different subwavelength structures, and these structure sizes usually of the order of half a micron. So there are people try to make these kind of structures, what try to localize light at small spaces, which is called a resonances or cavities. It's like in quantum mechanics, you must have studied trapping the waves in a 1D box, similar to that. So similar to here, if you try to trap light at a small potential box or something similar to that, and people try to do make structures to do that. And there is another structure which is used to manage light at the subwavelength scale, is called photonic crystals, which we will be talking quite a lot today. And the fundamental principle that works here, it's not something rocket science. It's very simple Bragg scattering or the Bragg diffraction, which probably you must have studied in even in your BSc level. And there are many other structures which use what's called a multiple scattering of light. Means there is no preferential direction for light scattering. Light is scrambled like a crowd, right? There is no ordering. Okay, here you can see the ordering, and you can create some kind of disordered pattern and get multiple scattering. So as a definition, what the take home message is to for nanophotonics is to create, the manipulate and detection of light at subwavelength scales. And why we need to do that? What is the problem if you don't do it? So you can strongly confine the light, which has huge technological applications, and there are many devices and things are in market. And you can slow down the light. Now, what will happen if you slow down the light? You can increase the light matter interactions. And in a way, you can modulate the flow of light. You can control all the technology that we have, because the way you can control electrons using semiconductors, right? So imagine a situation, can we control photons in the same way? For that you need a photonic band gap, like electronic band gap or your semiconductor band gap. Okay, and that was the main idea behind the development of nanophotonics, and it has given a lot of technologies, a lot of applications now. But and also it is now very quite excited in the quantum technology, which I will just show you one or two slides at the end. I will keep it this topic for some future discussion. Okay. Okay, let's move a little more technical. So where does it all started? Okay, so probably you can, in my opinion, um, the wave propagation, not only light, in terms general as a wave, it can be any type of wave, acoustics waves, de Broglie waves, or electromagnetic wave. It all started with a famous paper in Lord Rayleigh, published in 1887. Okay? So these are the actual text which I copied from his published paper. Okay, so this English quite different than that we use nowadays. So he considered a medium which we call a laminated medium, and it's a lamination means it's a kind of a periodic medium. You take one material which is like a black color, and another is a gray color, and which is periodic. Okay, and this can be a refractive index. You take a two material here which has a refractive index 1, and this has a refractive index 2, and you just periodically arrange it in one directions. So this is periodic system which has a variation refractive index. You can have a periodic system like Young's modulus, or for that will work for some or acoustic properties, or the well-known periodic system you studied, even if you're not, is a semiconductor where atoms are periodic. And these atoms are periodic. It has a periodic potential. And you've done in your solid state physics using Cronin-Penny model and many approximation. You solve Schrodinger equations and you get allowed and forbidden solutions. And those solutions give you band gap and propagating states and so on and so forth. So similarly, this all started with this paper where Rayleigh considered a periodic structures and some land. He trying to understand, okay, you should remember I'm talking at 1887. He's trying to understand the theory of colors in thin plates. And he basically trying to suggest in his papers that each of these material will reflect a little amount of light or little amount of wave, but the total reflection will be very strong, and you see that nice colors coming out of the structures. So that means if you send many frequencies from left side to right side, certain frequencies will be comebacks and be reflected back very strongly, like partial reflection from various loads. Various loads means each of these material will occur in phase, and the result must be a powerful aggregate reflections, even though the individual reflection of the material or the system will be very small, similar to Bragg diffraction you study. If you take one layer of atom, you may not have a two layer of atom, you may not have a stronger reflection or strong Bragg diffractions, but you have many, many layers in the Bragg plane where you get a very huge reflection at the right interference conditions. So Lord Rayleigh, even 1887, trying to put an idea forward. So Professor Raman was trying to understand the title of the paper, you see, the origin of the colors in the plumage of birds. So he tried to understand why these birds show either colors, sometimes the color which the bird changes the angle, the color changes, or sometimes whatever direction you look at, the color doesn't change. So he, Professor Raman said in his paper in this abstract, the iridescent type in which color change very obviously with the angle of incidence and observation, and there are non-iridescent colors, right? The color will not change whatever way you take a piece of color in your hand, it doesn't change whatever angle you look at it. But certain birds show colors, like peacock feather for example, it show different colors at different views. And he wrote another paper in 1935 on iridescent shells, certain seashells which shows these kind of nice diffraction colors. And he also write in his abstract the laminated structure of this structure, basically just similar to what Rayleigh wrote in 1887. So Professor Raman was even at that time, maybe these are the nowadays we call it nanophotonics. So people have been at that time thought about, curious about why does this kind of coloration comes in these systems. And later the field was a bit silent, and 1972 there was a paper published from Russia, and it is 1971, and it comes with more than a curiosity of colors and other things. It become more and more physics and technology. So spontaneous emission by an exciter. So you see the title, spontaneous emission in a periodic structures. So as you probably know that in 1935 Einstein have the Einstein A and B coefficients, and people know how to make lasers. And 1960s onward the laser was invented, and it's the 60s 70s, a time where the optical fiber has got a birth because the laser is available, so people are able to guide the light. And soon after the development of lasers, there is an urgency how to control spontaneous emission from light sources, because laser work on a principle called stimulated emissions, and you don't want spontaneous emission to happen in a lasing system, because and spontaneous emission is considered as a noise. Okay, it's something which some to be avoided. But basic quantum mechanics says that you cannot control spontaneous emissions. And if you studied, at least in MSc level, you must have studied in time-dependent perturbation theory, the Fermi's golden rule, which says that the spontaneous emission has to happen. That where you can control spontaneous emission, because it's somehow related to the vacuum field fluctuations. Okay, and if you're not studied, probably if you're a physics student, you'll study that in at least in Griffith quantum mechanics book. There's a chapter at the end called a time-dependent perturbation theory. Okay, so some of this I'm talking today is something similar to those theory you study in those books. Okay, so the whole idea that Baiko was trying to understand how to control spontaneous emissions. So he considered that you take an atom or a molecule which emit light and try to put it in a periodic structure or kind of a laminated structure. And this structure can control the emission of light. And later in 1980, when another paper published from MIT, where it showed that in a different system, that you take an atom, for example, this atom is emitting light, you try to trap it in subwavelength cavities. Okay, basically when I say subwavelength is lambda by 2, the size of this cavity is lambda by 2. Lambda is the wavelength of your design. It can be 500 nanometer or 2 microns. So Okay, and this is another theoretical proposals where we can control the light propagations. People still do not get much attention to this work, and if you look at the citations to these papers, it's quite small. Then later in 1987, from the Bell Labs, you can see most of these papers are single author papers in a day where we talk about collaborations and 100,000 authors in each paper. So a paper came from Bell Communication Research, was titled "Inhibited Spontaneous Emission in Solid State Physics and Electronics." So he put up the same idea in a very perspective, in a very different technological ways. Okay, so his whole idea is to see this is equally true in the solid state, where spontaneous emission plays a fundamental role in limiting the performance of a semiconductor lasers, heterojunction bipolar transistors, and solar cells. So he was also looking how to control spontaneous emission, and he proposed this kind of system which is periodic and which can tailored so smartly that you can create a what is called a photonic band gap similar to electronic band gap or semiconductor band gap. And if somebody can achieve that, it's probably we can control spontaneous emissions. And when you say control spontaneous emissions, what you study in the books and all that may not be right. Okay, so which teach you that it cannot be controlled, but it is something which can be controlled. Okay, so this is all about the historical perspective, how this field, how people thought about nanophotonic structures, and at those times, no word called nanophotonics, and because all are theoretical proposals. It's a nice to read this paper even for students because there's no mathematical equations or one graph at least, and it's like telling you a short story to you. Okay. So let's get more deep into the technical what's all happens. And we are talking about the light matter interaction. So the light propagation to a structure, which is a laminated medium or some other crazy structures. And we know that when we talk about light or photons, we have to work with the Maxwell's equations. And these are the basic equations, which I'm sure everybody in the audience knows or remember it. And in your Griffith or electrodynamics course, what you do is you write this equation for a free space or a given medium, and you write a plane wave solutions, and you get a wave equation for light and wave equation. So I wrote it for electric field. You can also have it for magnetic field. Sorry, there is a vector symbol is missing. And so you substitute a plane wave solutions with a k wave vector and omega is a frequency of the light, and you solve it and you get a frequency versus wave vector relation. A simple formula to remember. Okay, your spinal cord can tell this formula omega equal to ck, and it's a straight line relations. When you did your quantum mechanics or when you study your solid state physics where you have a free electron model, you have a frequency versus wave vector is a parabolic relations, not a straight line. And because you solve Schrodinger equation for dipole waves and you get a k-square dependence there. And here the relation is called linear, and this is what we call light line or the dispersion curve. What is mean is that if you send a frequency of this light at this frequency, there is an allowed wave vector so that it propagate to the medium. If you send this frequency, it has an allowed frequency or allowed wave vector and it propagate to the medium. So this dispersion relation or the omega versus k is like a horoscope of a material or a system you have. So if you solve Maxwell's equation for a crazy medium you have and you get these allowed or solutions, then you can predict by looking at this graph what this structure can give you when you propagate an electromagnetic wave through it. And the reason you see the light coming through a glass window in a transparent sheet, because all those medium obey this frequency and wave vector relations. And if there is something happen to that medium, this relation change and there's a frequency may not propagate through it. And that's what we are going to do it in a couple of minutes. Okay, so now we have gone from Maxwell's equations in a single medium or a free space to a laminated medium, which all these great people considered. So you consider a medium which consists of two dielectric constants or two refractive indices, epsilon 1 and epsilon 2. And this epsilon 1 is greater than epsilon 2. And this refractive index is periodic in one direction. So you can see that epsilon x equal to epsilon x plus sorry, here it is d, actually is a and d are same. So this is a periodicity or the repeatance, the unit cell it is repeating. So you can consider epsilon 1 and epsilon 2 as a one unit cell, like in the crystal terminology, and this is periodic in one direction. And for simplicity, I'm only showing for one directions. And if you simply write your wave equations, which you studied, probably you may not thought like this. The dielectric constant, which you keep as constant in your textbooks and what you studied, now is a function of space. That epsilon, when light goes from left to right, it has C epsilon 1, then it's C epsilon 2, then it's C again epsilon 1 and epsilon 2. And this dielectric constant is not a constant now, it's rather a function of space. One space means one spatial coordinate. And now it become very difficult to solve. You cannot do it even in by hand. You need to even have standard numerical codes and softwares are nowadays available to solve it. Okay, and if you solve this thing, you plot the frequency versus wave vector diagram, which I told you that it's a horoscope of the medium. And this is the green dotted line is the for the normal medium, and for this kind of periodic structure, the red and this blue curve is the result you get. So you can see that at lower frequencies you don't see much changes. Okay, things look very similar, but when it comes to this yellow region, there are certain frequencies there is no wave vector. So wave vector is like a passport, like a visa, you can go to this medium. So now if you launch this take this medium and launch these frequencies, there is no wave vector here. The dispersion relation got a break here, and there is no allowed wave vector. So what happened, these waves will simply diffract or simply reflect back to you. This is similar to what you study in semiconductors. So you have a band gap and there is no block mode, there is no solution available in the band gap. Similar, this structure will give a frequency gap or a stop gap, but for light frequencies, the light which you see around us, the light bulb you see in your room. Okay, so that's why we call this is a photonic band gap. So simply you take this medium and you launch the light or different lambda, let's say lambda from 100 to 1000 nanometer, and this light will reflect back. Many light will propagate, like these frequencies will propagate. When you come at the right frequency, when I say right frequency, the frequency which satisfy the Bragg condition, which will be reflected back and which cannot propagate to the structure. Now, if you have this kind of system in your hand, this kind of material, they'll show you colors. The colors are reflecting because that light cannot propagate to the system, and that's what the peacock feather show you nice colors, because those blue or green, orange color which cannot propagate to the structure because it's incident from sunlight and it cannot propagate to the medium or the peacock feather, it simply reflect back to you, and that's what we call stop gap or the frequency gap or photonic band gap. So I may use these words coined indeterminately in the talk. So how do you know that whether your system has a photonic stop gap or not? So you make these structures, mostly these are man-made structure. You make this structure and let's say I give you this sample. So what you do experimentally or even theoretically, you calculate the reflectivity spectra. So the black line is the reflectivity spectra, which give you 100% reflections around 1.5 micron wavelength. And simultaneously, you measure the transmission of the light. You can see that it theoretically or ideally gives zero transmission of light. So you do an experiment, you have the sample, you launch light from let's say 1000 nanometer to 2500 nanometer. Certain wavelength or certain frequencies are strongly reflected back to medium. And this is the way you characterize your system, your sample. And my talk will be more experimental. I'll show you how we do it in the lab. And if suppose and you calculate, you solve Maxwell's equation and you calculate an electric field intensity at this band gap frequencies, and you see electric field intensity as a function of number of layers. The number of layers, what I mean is this number of layers. So it can be 10, 20, 100 as you wish. And you can see that the electric field intensity is exponentially damping into the structure. So if you remember your condensed matter like solid state physics, this is a situation which you study in your books called the block wave vector is imaginary in the band gap. There is no, the field is attenuating, the block wave is attenuating in the band gap. And because in the band gap, there is no states available. So that the light is not allowed to propagate too far distance, okay, maybe 25 layers, but the intensities get almost zero by 10 layers, okay. So this is the basic concept of how these colors occur in nature, how you, the basic things about nanophotonics. You engineer your structure in a very interesting pattern and you play with the light. You either reflect it down or you completely make it absorb or change the angle, change the polarization, so on and so forth. So what I shown you in the previous slides is very simple one-dimensional system, okay, that may not be very exciting, okay. So what we need is more like a 3D system. So in a two-dimensional, you can think of, you take a material and you make these holes, and this is the air holes which is periodic in one direction, and in this direction also it is periodic. Okay, so this is air material, and here air material, and this is kind of like a two-dimensional periodics or two-dimensional laminated structure. And this is a real fabricated sample in the lab where you can see that this is air holes, which is periodic in this direction, also this periodic in the second directions. But in the third direction, it is constant, either it is air or the material. And this is a three-dimensional periodic structure you can think of. You take a piece of blocks and you make holes like this, the first hole, and you just make a perpendicular to that, and you can create a 3D structure. And this is a real example of a structure which made in laboratory, and where it shows a periodic variation refractive index in all directions. This is a structure actually that paper, the Yablonowitz considered that if you can make this kind of structure, and then spontaneous emission can be rigorously forbidden. So now you may ask a question that, okay, we know everything in X-rays, we know Bragg diffractions, and we know all these things, and you go from an X-ray wavelength to visible wavelength. The physics is more or less same. What's the news? What is great thing about this? Why you do all these things? The answer is, if you take a photonic a crystal or this kind of periodic structure, and you send light, it get diffracted back, then means that light cannot propagate. It has stop gap in all directions. Now imagine you keep a light source inside. Okay, you keep a light source inside and you excite it, and this light source is, let's say, emitting at the band cap. This light cannot propagate because which is in the band cap. So what happened is that it has an internal Bragg diffraction. It somehow you trap this light inside the structures. So you are standing outside and you see there's no light is coming. Even though light is emitting from the source, the emission is forbidden. So this is a system. Then using this photonic band gap, we can make the spontaneous emissions absolutely zero in ideal theoretical perfect case. Okay, and this was the great moment or the great thing with this kind of sample, that if you have a band gap and you have a light source which emit at the certain frequency, certain lambda, and you make it equal, the light emission can be rigorously forbidden. And what happens if you can you learn from your books probably. So you have a band cap, then light cannot propagate, then you keep a light source, and then it will excite, the light cannot propagate. So the textbook knowledge you have is you have a two-level system, you have some atoms in the ground state, you excite, and it cannot now come back because you study in books after a few nanoseconds it will come down. Now, if you do this experiment within a photonic band gap, the light emission can be forbidden at that frequencies. And this is a formula which I said you will learn in quantum mechanics, like the decay rate of an atom from the excited state to the ground state. It depends on dipole transition moments, and it also depends on a parameter called density of photon states. And if you look at in these structures, the density of photon states at the stop gap or the band gap, the density of state goes to zero. And if the density of state goes to zero, the decay rate is zero, and the lifetime goes to infinite. So the emitter cannot come down, it stays there forever. So in a way, you can control the spontaneous emission system. Now the question is, how do you make these structures? Okay, it's very, very difficult to make these structures. Okay, experimentally it is a really challenge, and even the last 10 years, people got many success experimentally to make sample. So we followed very different methods, not the semiconductor fabrications. We use what we call colloidal suspensions. These are microspheres of diameter 280 nanometer, and we learn from the chemist how to do this. And we have some kind of suspension in a glass substrate, particular angle. It kept it in oven, and it take 1 week to grow the sample. And after maybe a week, all the suspensions are evaporated because it's in a temperature oven around 50-60 degrees centigrade. And then slowly these particles go and settle on the substrate, and it give a nice 3D arrangement of the microspheres. Okay, the only thing you should remember that the diameter of the sphere is 280 nanometer. It's such a small system. And let's say you grow the crystal, you take the out of your sample and you put under a laboratory light, you can see nice colors it coming. That one signature that the crystal is grown. And you can see that the beautiful coloration, something like a peacock feather I shown you in my very first slide. Okay, so this clearly shows that the sample is grown nicely, and it will show you diffractions in the visible light. Okay, so we grow the sample, and once you grow the sample, you look at how the ordering or how the structure look like. So we do what we call is a scanning electron microscope. Basically, you are taking a photo of the sample, but at the very high resolution. Okay, so the sample look like this. It's not that clean. There's a lot of dirt, lot of cracks, these kind of things it happens. And if you zoom to some region, you can see very nice ordering of these spheres. And this is a bit more zoomed. You can see the top layer, then beneath there is another layer. And if you look at this crack, this is the way it look like on both sides of the crack. You can see the nice ordering. So it's look like an atoms are arranged periodically. Okay, these are not atoms. These are my microspheres, with the sizes of 280 nanometer. So this is a three-dimensional structure. You have the material and there is an air between. The space between these spheres is the air, which by default act like a second medium for me. So I have a periodic structure not only in one direction but in all three directions. And this structure will show you some interesting things, and I'll show you now. So suppose I make the sample. So what I do, I need to see whether it has a frequency gap or not, because you see nice colors. Just because you see color does not mean that you have a nice optical properties that we look for in the laboratory scale. Okay, so we would do a simple measurement. You measure reflection, which is a blue line here, and transmission is the red line. You can see that there is a peak in reflection. There is a trough in transmission. That means wherever light is got reflected back, the light cannot propagate to the structure. So this is a photonic stop gap or a frequency gap, and that's why you said color. And we made many samples, and you can see that I can tune this band gap wherever I want, depending upon the lattice constant or the sphere diameter I have. So if I use a larger sphere diameter, I can even get a gap at 1.6 micron, or I can use a smaller one, I can get it close to 500 nanometer. And we just compare our data with the theoretical calculation, and you can see that like a band structure you see in textbooks, our measured data is in quite agreement with the calculated one. And this so very interesting thing. If someone is interested, you can look at papers published in the last few years. And now there is a problem that I show you that if somebody must very crudely looking at, somebody can argue with me, well, you have a nice sample but your reflectivity is just close to 60%. It's not going to 100% reflections. Where does the light goes? There a lot of light is lost in your experiment or in your system. And the reason that we found out after a lot of brainstorming, the reason is these kind of tiny cracks coming here. Okay, so in this measurement we are using a large beam to measure the reflectivity. So all these nasty things are actually coming into our measurements. So the question is, can we avoid all these things and just measure from a smaller region? And that is a very big challenge, because you look at the scale bar here, it is 10 micron. So this size of this area is probably around maybe 100 by 100 micron or smaller than that. So how can we measure reflectivity from such smaller regions very nicely? So we developed one setup at our institute, and this setup is now published in a couple of years back. You can mimic this in your laboratory. So we made a setup where we can go to a smaller region of the sample. So this is a typical picture we take in a camera in our setup. You can see that this is probably around 10 micron length. Nanowires, there's a laser is focused here, and you can see that we can go to a smaller region and measure reflectivity from that. So with this, we measured and the reflectivity for our sample, and what you see is the blue line is the reflectivity using our new setup. And now you can see that for the same sample we get close to 100% reflectivity. And why we get 100%? Because we avoided all these unwanted thing in our experiment, and we measure from a smaller region here. And if you do conventional measurement, what mostly people do, and you can see that it gives around 50% reflection. So we call these are single domain measurements. Keep this word because I'll be using quite a lot in next few slides. When I say single domain means some region which has no defects or no disorder, very beautiful area of the sample. And we measured many domains like that, and we could find that the thickness of the sample actually varies when you move across the sample. At some places you have around 18 micrometer thickness, and in some places you get close to 9 micron thickness. And this kind of minute measurement with a lot of effort and pain has a really consequence on the kind of physics we understood, and the application that this kind of system can provide. And also we were just doing some fun in the lab. We took a peacock feather, and we want to see whether we can measure it. This is a peacock feather. If you look at an optical microscope, when I say peacock feather, you take a one barbel out of it, one colored region, and this way look at in the microscope, optical microscope, what you see in any pathology lab. And if you look at this feather in my lab, with the setup we have, you can see that the laser is focused on one small stem of this peacock feather, which is probably a 50 micrometer by 10 micrometers. So you can focus there, and we measured, and you can see that it gives you nice reflectivity, and the different colors you take, it gives you sometime close to blue color, sometime green color, sometime close to red color. And you see this, when you keep arrays like that, you get like a very nice colored pattern. Okay, so this is what the photonic band gap or photonic stop gap is all affected. So once you made these photonic the structures and photonic things, so the next plan is to see whether we can control spontaneous emission of lights. So what we do is here we take some emitters like dyes, quantum dots, molecule. Okay, if you are not too much, don't worry too much about it. You have something which emit light. Okay, let's say light bulb of small size of which can go into the sample, which emit light. So we keep the light source everywhere in the sample, and we have designed a setup in our lab, and we go to a domain to do the measurement. So if you measure these emission spectra or the what is called photoluminescence without any material or anything, okay, you are this is the black one is the spectra of your light or your bulb, okay, which is just like you are keeping in your hand, okay. So it get this kind of spectra, which is the black one, the normal one, nothing changes. But when I measure, when I put this bulb inside my material, inside my structure, and it emit within the band gap, and I measure from the smaller region, you look at this blue curve here. You can see that, forget about the red for a moment. You can see that now the spectra is quite different. Where I supposed to get maximum light, when I put inside structure, the emission intensity is quite reduced. And that is because of the band gap, because the emitter is trying to emit at these frequencies, but the structure is not allowing. You may argue that, yeah, still there is some light comes out. Remember, these are real samples, okay? These are not ideal, the perfect 1 weeks. And if you divide this blue divide by black curve, which we call intensity ratio, you can see that if there is no structure induced changes, you should get unity emission. But because of this structure stop the light, you can see that the intensity ratio actually goes to close to 60% suppression in emission intensity. And now the question is, do you get this kind of suppression, also the control of emission at everywhere the sample? The answer is no. Okay, so we do these kind of measurements, the separation, and we plot like in a histogram. Then you can see that there are places where you get a very low separation, and there are places you get a very large separations. And when I say how you move here, for example, this domain may be correspond to here, and this may correspond to here. So we do this kind of many measurements, and we see that where our system shows a real separation of spontaneous emission. Okay. Now, what I said is that in the initial talk, like initial slides, that we need to look at the Fermi's golden rule, whether density changes or not. So this is what you know from textbooks, and this parameter rho, which actually characterize the density of photon states. And if you are still not heard about density of photon state, is the states which are available for a light to emit, or the light can communicate to the medium. And if there are systems that large local density of states or density of states, your large, suppose your light is emitting, it has large pathway to propagate to the outside world. And if you reduce the L dose, the light has only one way to go, or maybe no way to go. And typical experiment we do in the optics to measure the density of state is the lifetime measurement or the decay rate measurements, where you excite the molecule to the atom to the excitation state, and you look for the time it take to come down. Okay, so you must have learned in textbooks, right? After a few nanoseconds, the atom from the excited state goes to the ground state. So you excite the atom, it goes to the excited state, and you wait, and it comes down, and probably in a time of around 6 to 10 nanoseconds. And when intensity is almost reach zero, that means all the excited atoms goes down to the ground state. Similar thing have you studied in radioactivity, where the decay happens of the hundreds of years or thousands of years or millions of years, but in optics things are very fast. Things happens in nanosecond or picoseconds, the decay rates. So we did develop an experimental setup to measure whether we can measure this lifetime or decay rate from the samples. And this is a typical experimental we do. We measure the intensity as a function of time. Again, to understand, you have a ground state, these molecules, the light source in the ground state, we excite, it goes to the excited state, and we're looking the time in a watch, which can give times in nanoseconds, how much time it take to come back to the ground state. And this black curve is the black symbols is a reference sample. That means there's no band gap or anything, and give you typical lifetime of the system that we expected for the typical decay rate. And when you keep this light source in a photonic band gap and try to measure the decay rate, you can see that now the decay is not that faster, it's getting slowed down. Like light has a difficulty to come out, right? Somebody stopping it, don't go, something like that. And that happens because of the band gap. And you don't get an ideal one because these are real samples. And by fitting these curves, we can get the lifetime, which you study in atomic and molecular physics, lifetime of a level. So the lifetime typically for these kind of emitters is 1.9 nanoseconds. And by putting that emitter in a photonic band gap, we got a lifetime of 4.3 nanosecond. You can see that the changes or the increase in lifetime. If the lifetime increase means the atom or the molecule is staying more time at the excited states, and it's not that fast, it really slow down. Now the question is similar to intensity, that do these lifetime is same everywhere on the sample? Again, answer is not correct. Answer is no. So if you do this kind of measurement of hundreds of domains, I hope you remember what I mean by domain. At different wavelengths, at 570, which is not a stopgap, and 600 is a stopgap, you can see that the lifetime correspond to stopgap wavelength is always higher and compared to the reference wavelength. But if you're so unlucky experimentalist and you did an experiment where you choose this domain for your experiment, and you can see that the reference wavelength and the band gap wavelength give the similar lifetime. So the same sample, there are domains which does not give you any emission control. So you have to really work at these domains where you can control the spontaneous emission of the light sources. And what we find out is quite excited that in our community that this lifetime is not simply very arbitrarily. It has some scaling. It has a linear scaling with the thickness of your sample, okay, or thickness of your domain. As you increase the domain thickness, the lifetime is increases, and which was recently shown in a theoretical calculation by a group in Netherlands, where it's published in Physical Letters, where they show that the density of states scales linearly, and the density of state is related to lifetime. So in experiment, if you want to know whether the density of state changes, you have to do a lifetime measurements, and you can see the lifetime is linearly scaled. So in textbooks, you learn LDOS is depends on frequency and position, but what we propose doing our experiment, that it's not only depends on frequency and position, but rather it also depends on your system size or the thickness of your nanophotonic sample. And this was very nice results, and this published in optic letters, and then followed by a real very detailed paper in physical review in the last 2 years back. And so probably with everybody will worried what are the use of the system, what are the applications. One of the great thing about photonic band gap or photonic crystal or this kind of structure is the fiber which made of photonic crystals. So this is a typical example of the fiber which made of photonic crystals. So and compared to our conventional fibers where light transmitted through a total internal reflections, and you need a high index core medium for that. But here, if your core is an air, you can propagate the light, because the light is now trapped not due to internal reflection, but rather due to the periodic structure in the cladding, which give you the photonic band gap, and the light is trapped inside the core. And there are microcavity lasers, or what's called nano lasers. There are a lot of sensors developed on using this, and quite a lot in the recent times. These structures are used for quantum technological application, where you can generate on-demand single photons and entanglement, spin photon interface, and many quantum technological things, which can be used to can be enhanced using these kind of structures. So before I just finish, I might not take much time now. So in the till now, what we see that we are always interested in ordered system, right? So I don't like the disorder. I want to be perfect system as much as possible, and everything is nicely ordered. These microspheres or the periodic refractive index is nice. And what I'm going to do now, I'm trying to create some kind of, certain kind of disorder in the system. Okay, and it turns out that disorder is sometimes better than order. Okay, and everybody is disorder, like human beings. A defect or disorder make everything is interesting, right? Or maybe my lecture also sometimes interesting, maybe because of the disorder in it, and the people or the nature, everything become interesting because of disorder. And what we are not talking about is not an arbitrary disorder, what we call is a tailored disorder. So it's quite people put their eyebrows up when we say Taylor disorder. How can you tailor a disorder? Disorder is a statistical process. You can't have much control on it. But I'll show you how we do that, and we can create a disorder in a very controlled or a very engineered way. Okay, and it was give you some nice things. And whether you notice or not, disorder is everywhere. The one famous thing you learn from your school days is the the color of the sky, the white, these things, so multiple scattering of light. Certain these animals, the bees and butterflies, has this in their body very disordered structures. And recently we had a paper published on how butterfly scales or butterfly wings shows white colorations and how the light is propagating or diffused to this system. So we apply even mathematical models, a theory to butterfly wings, and it'll be nice for students to look at those papers. And some of these nice coloration happens due to the some kind of disorder structure in their body. And this kind of cicada wings and all, they have a very disordered structure if you look at a microscope, and that actually kill the bacteria and what's called a punching of this bacteria, and they so that they can survive in this. And if you look at the paper published in Nature and PNAs and all about how people understand, trying to understand how these colorations and beyond some scientific curiosity, beyond and to make this system for technological development and breakthroughs. Okay, so just one slide, probably those who do not an idea about disorder system. So basically, ordered system, the refractive index is periodic, and in a disordered system, refractive index is random. The random variation refractive index, just like a crowd in a festival or a crowd in a road watching some shows. You can see that if you take every person as a scatterer or every person as a material, and every people are very randomly arranged. There is no order, preferential ordering in them. Okay, and simple example that the paper, white paper, chalk powders, your paracetamol tablets all look opaque white because the light is scrambled in the system. So if you have a disordered system where there are a lot of scatterers, you send the light, it get multiply scattered, and the scattering between two events is called scattering mean free path. And after certain distance it loses its memory. Basically the light does not know from where I came. Okay, it's like a drunk person entering a crowd, right? He will scatter here and there, and after some time he does not know from where I came, which path I took, so he loses memory. So similarly in a scattering medium, the photon loses its memory. When I say memory, means its phase, its amplitude, it has no correlation with the initial positions. Okay, and we say light is now randomized, the propagation is random, and it's like a diffuse, it just person goes like this, so the photon also goes like that. And then you apply diffusion theory to solve the solutions of light waves in this medium. Or typical example is that in our lab, you can see that our IIT symbol, it's a very nice transparent glass now. We create bit of disorder in that. You can see that things become white. And if I increase the disordered material, it's completely opaque now. It look white. You can't see anything. The light is getting, it's getting now multiply scattered, and you cannot get any reflection back the proper. So we made these structures using our microspheres, and we did some chemistry into that. And we can see that if we very crookedly look, you can see that some region there are some ordering here, a bit of small ordering here. And so we could engineer this kind of small ordering within the disorder system. Okay, and how do you know that there is a really a disorder? Because people sometimes don't agree with these pictures. So what we do is a pair correlation. So we take 1 points and we see who are the nearest neighbors. Okay, so we take starting with this point, for example, there is a scatterer here, there's a spear, there's another spear here, there is another spear here, another spear here, and it completely dies off after that. So we have some kind of ordering till 1 micron on the lamp sample, in the sample geometry. And if you have a powder sample, like you don't have these kind of spherical particles, and you can see that pair correlation function, which completely there's no oscillation here, because there's no, we don't expect any the ordering in the samples. But here you see a bit of ordering, and what we call is the short range order in the sample. And what was surprising to us is what was we consider quite great work. So when we measure the transmission of light or the reflection of light, so we measure a total transmission as a function of wavelength. And I'll tell you why we use a total transmission here. Usually when you see light or transmission of a light through a glass window, you see what you measure is a ballistic transmission or a straight transmission. But when you have a disordered medium, the light can go in all directions because it's a multiple scattering. You may not get all the light coming straight to you. Some light goes here, some light goes here. So we have a setup in our lab where you have a sample here, and there is an integrating sphere here. So light will go in all direction, which is captured by this sphere and put it in optical fiber, which is taken to a spectrometer. So that's why we collect total transmission. Basically, collect all the transmission channels in the backside of your sample. And so if you have a typical disorder sample like a powder or a paracetamol tablets, you measure this experiment we did in the lab, you get a sim with decrease in wavelength, the transmission is decreasing like a Rayleigh thing. But when we did on our this sample, which is we call it as there is some short range order in this system, and we see something interesting. The curve is quite different. It shows the trend that expected for a disordered medium, but at certain frequency there is a dip come in transmission spectra. So we were a bit surprised initially, and then we made different samples, and it has a good scaling. Okay, if I change the diameter, this dip is actually scales with the diameter. And then we did a lot of theory, and skip all those things today. And we understood, because of the short range ordering, this short range order induce a frequency gap similar to your periodic system. Now, how do I know that it is the same like periodic system? So we fabricate a long range ordered sample, which is a photonic crystal or the photonic stop gap, and you can see that it comes nearly at the same wavelength. So by engineering the disorder, creating short range order, I can create these kind of similar features in a disorder medium, which is something which nobody could believe initially. And we published quite a couple of papers back to back in physical review on these kind of new experimental observations. And now we are doing many experiments, not only with these kind of sample, even with the bio-insert system like butterfly wing scales and all, to understand more about how light matter interactions. So give me 2 more minutes, I'll conclude it. So this is all about nanophotonics I wanted to share with you. Then I thought yesterday to show you something which is quite recent. Quite recent means happens in last couple of months, where the world is moving towards quantum technology. And like India, the country, we are talking quantum computer, Amazon has a quantum computer, IBM has a quantum computer, and so on and so forth. So one of the essential thing for quantum communication or quantum these things is a single photons. You need to have a single photons, and not only have a single photon, you need to have a single photon of indistinguishable single photons, and you should have a own demand single photons. When I say on demand means I should get a photon when I want. It's like a pistol, right? I click it, I get a photon out. If I click it, I get another photon out. So we were quite fighting for the last 4 years or so, developing an experimental setup to measure single photon in our country. So this activity started around 2017, and we were succeeded just a month back. And we have developed, this is actual setup picture in our lab to characterize a single photon source. So we have a laser here, it takes the beam here, and it goes to a microscope objective. The sample is mounted here on a translation stage, which has a resolution of 50 nanometer. And you collect the emitted light. We take light here, and it comes here at good beam splitter, and the beam splitter split the light into one part here and one part here. Suppose, imagine for a minute, a single photon is coming. Suppose my system is emitting single photon, and the single photon take this way, it comes here. Now it has a 50-50 beam splitter. It can go either here or it can go either here. It cannot go to both detector at the same time. So this is what we look in our experiment. So somebody is standing here, not in person. There is a circuit or electronic here, which you look at this kind of coincidence where this guy got a photon or this guy got a photon. If both these guys, both this detector got a photon, it will register one. That means it is not a single photon. There are more than one photon. That's why both got photons. Suppose if the single photon, it comes here, it can either go to this one, let's say, it got a click, and this guy say, I did not get. So now this count, this will say 0. That means both did not get the photon. So we look at this kind of coincidence count and how to measure. This is what called in quantum optics called Hanbury-Brown TIS experiments. Okay, and this setup is can do many things like confocal mapping, micro PL, and so on and so forth. So we have some sample, what we call atomic defects in diamond. So you assume that there is some kind of a defects in a perfect diamond. Diamond is made of full carbon atom. You throw some carbon atom, you create a vacancy, and close to that you create a defect or a nitrogen kind of thing. So these are these kind of single photon sources which is lying on the sample. These scans are done maybe less than a micron by micron, and you can see that there is some emission here, there is some emission here, there is some emission here. So this is what called confocal map. This is we developed here, and we look at the whether light is there. We have to see, yes, there is some light emission happening because we are getting photon counts in the detector, and we measure the decay rate, how much time it take to the to the ground state, which also happens in the order of 10 to 20 nanoseconds. And this was I was very excited to show this. So we measure this coincidence count, that whether we have a single photon, and at this time there are more than one photon, there are more than one photon, more than one. At this time, when both detectors are same time, it shows a dip. That means that there is no coincidence, and this dip is actually what is a signature of a single photon emitting from your system. This is what we theoretically calculated using rate equations. At zero time delay, you should get a dip that characterizes single photon, and that's what precisely we measure here. And it was really a great experimental discovery for us, probably the first time in our country that after around 4 to 5 years of effort, we could not only develop the setup and we could measure. And so I just want to show, because many students are there, this is what where the technology or the photonics is now taking, where these kind of sources which can emit single photons is combining with nanophotonic structure and what we call is quantum nanophotonics, where we can do not only a lot of fundamental physics as well as many technological breakthroughs in that. With that, I conclude. I hope I able to convey some charms and some of our understanding about nanophotonic structures, how these colors comes and what is its use, how we characterize, how it related to the textbook thing, what you studied, and how it comes into how we scale it to research level and with new inventions. In case if you don't understand anything from my talk, please look at our papers, and everything is much better explained. And these are the important key results which we discussed today. And I give talks, almost 2 talks per month on an average, on many topics. So work actual heroes, actual people who works in all this behind me is my students, and these are my current students. There are 5 PhD students working under me along with the postdoc. And these are my alumni from my group. First student, she's now a scientist at Quantum Bridge Technology in Canada. Sachin, Sudhir, Meka, they're all doing postdocs at US and Netherlands. And several master students. We get an excellent master student from our institute, also from ISIS. They even publish paper, their projects, and a lot of interns from Indian Academy of Science, which help me to give some kind of challenging problem which I have no idea what going to happen. So these are good experimental, not only the topics, also the students, so whether that field will work or not. So Indian Academy of Science and many interns and collaborators from Jammu here in India, and I missed some people here, I'm sorry for that, from University of Stuttgart in Germany. And being an experimentalist, a lot of money we need. And I thank all these funding agencies who are generously funding, not only from India, also from German National Science Foundations, Joint India-German Project, the Russian National Science Foundation for the Indo-Russia projects, and other agencies, and especially my institute, who give me all kind of support. And these are group right now. Okay, this is me. And these are my PhD students. It's taken a few, the student graduated last week and she's in Netherlands now. So we took after her defense. And thank you for your time. And if you have any questions, I'll be like to discuss.
Thanks, Rajesh, for the nice presentation, and congratulations for the first single photon source that you developed.
Yeah, thank you.
So the session is open to questions.
Either they understood completely or they don't understand anything.
I think one question from my side regarding the emission study of the peacock feather. Okay, just the peacock feather shows 30% reflectivity, something like that. With your setup. So why this is also due to the structure you got in your nanosphere, like the fractured structure or something like that.
So I think what I understood is your question is why this peacock feathers show 30% of reflection.
Yeah.
Okay. The reason is that compared to our structures, the refractive index could be very smaller than our structure. So this refractive index contrast also decide the reflectivity values and also the thickness of this thing. Probably these feathers are very thin compared to our sample, and or maybe there may be unwanted scattering which you could not control. Okay. So that could be the reason why we got 30%. We also puzzled by that why it did not give much larger values, and it's also quite broad peaks. So we were having this funny ideas to trying to put some NV senders on these things and to see whether we can get a single photon mediated by the peacock feather.
Okay.
And so we were just they have discussions that whether it works because it's only show 30% reflection.
Okay.
So yeah.
Maybe due to some randomness in the random
Yeah.
figure
These are
also
not.
you.
Yeah, correct. You're right, because these are not really perfect. And also when you take these contaminations and many things could be happen. And
Yeah. Okay.
yeah, there is a randomness, obviously.
So any questions, please? You can also type questions in the chat window. Hello. If not, let's move to vote of thanks session. I invite somebody from the student community to propose the vote of thanks.
A very good evening to one and all present here. It's been such a great honor to be part of this wonderful event today, and it is my privilege to propose a vote of thanks on behalf of everyone here. I would like to extend my heartfelt gratitude to our esteemed speaker, Dr. Rajesh V. Nair, for taking time out of his busy schedule and guiding us through this webinar. Sir, your teachings have enlightened and encouraged us in pursuing new ideas and has given us a lot of information about the field. Thank you, sir. I also thank everyone part of the organizing and advisory committee without whom this webinar would not have been possible. Last but not the least, I thank all the participants of the webinar for being a wonderful audience. I hope this webinar has benefited you all. I wish you all the best.
Thank you. Thank you once again, Rajesh, for the nice presentation. So
Yeah, thank you, Sajid.
So
See you.
okay, that's it.
Have a
With
great
this.
day.
So thank you. So this session is over. So
Yeah.
you please remember to fill the feedback form for your certificates. Okay. Thank you for your participation and thanks. Thanks all. Bye.